We have Jakub Szefer, Electrical and Computer Engineering Associate Professor at Northwestern University. Jakub Szefer, welcome.
Thank you.
And we just grabbed you right off the stage from a very interesting conversation about hacking quantum computers. In your lab, you're actually working on IBM real quantum computers.
Yeah, so we actually work with a lot of different vendors, and thank you to the vendors for letting us use the machines remotely. So a lot of the quantum computers today, although their size is limited, you can easily access them over the internet, either through some research credits or even by paying. And IBM is one of the bigger vendors, but there are many other companies from all different types of quantum computing, superconducting, trapped ion, neutral atom. So it's sort of exciting that they're available online, but also that creates a lot of the security issues that motivate our research.
Right. And so what are what is the quality of quantum computers or the imperfection in quantum computers because you're attacking with side channel. So which imperfections are you relying on for the side channel attacks?
Right. So we did a lot of work on crosstalk between qubits, which is sort of can be both used as a side channel, but also like for fault injection. So sort of the noisy qubits are, so when you execute some operations on one set of qubits, it affects adjacent qubits, and that's mostly kind of focusing on what's called a NISK, or noisy intermediate scale quantum computers, which is available today with few hundred qubits, where sort of the qubits are sort of not exactly perfect, and we exploit the imperfection. But a lot of the industry and research is also we do fault tolerant quantum computer, where they will sort of create these logical qubits made out of many so putting together many imperfect physical qubits to create a logical qubit, and that will sort of create maybe a little more protection because of the error correction, but it might also actually create its new security vulnerabilities. So we're focusing on these noisy machines, but also thinking about the upcoming fault-tolerant machines.
Okay, that makes sense. And just in the last year, there's been kind of a new series of attacks called double-sided crosstalk. Can you explain what those are?
Yeah, so a few years ago, sort of, we started looking at these crosstalk attacks among different qubits, and a lot of sort of initial attacks were in a way motivated by what we did in FPGAs, where one circuit is physically adjacent to another circuit, and so there's some interaction to affect the victim circuit. And so we applied that to quantum computers, where you have one quantum circuit affecting another quantum circuit, and
Or similar to a Rowhammer style
it is
attack.
exactly similar to Rowhammer style. And some people actually borrowed the name Rowhammer, and then they extended our ideas to having this double-sided attack, where now, okay, if you have a victim quantum circuit with two attackers on both sides, sort of creating more noise by sort of actuating qubits on both sides kind of creates more results. So there's people kind of exploring these new types of attacks from both sides, or maybe even attacks when the qubits or the victim attacker is more separated on the quantum computer. And I should highlight that a lot of the research focuses on sort of evaluating the scenario where you have multiple users on the same quantum computer, which is not yet available commercially. But there's a lot of sort of research and proposals, and maybe even debate. Should we or should we not offer?
You're arguing we may never be able to have or achieve multi-tenancy on a quantum computer because of this problem.
I think so. I mean, I think from classical security, we've learned quite a bit that anytime you have resource sharing of any sort, there's security vulnerabilities, and this multi-tenant quantum computing might just sort of it creates the situation where the attacker and victim can be next to each other, and maybe those security problems will really prevent people from deploying multi-tenancy. So we don't know. I mean, there's this tension. Can you get more utility out of a quantum computer versus security problems?
But you're seeing some people work toward like modular architecture or chiplets, and do you think there's a future in that?
I mean, definitely for the superconducting machines, quantum computer manufacturers are thinking about, or actually even working on actively on having the modular chiplet design. Whether that will be combined with multi-tenancy, we don't know. I mean, it would be interesting, or it'd be a natural fit that, let's say, one chiplet or a set of chiplets get assigned to different users, but then you might have new types of crosstalk attacks, which might kind of nullify the benefit. So we don't know.
Right. And so just to back it up too, this quantum is kind of this collision between engineering, computer science, and physics. And how do you think that interplays differently than classic computers?
I mean, I think definitely people are still figuring out the functionality of quantum computers. So, we need more qubits, better qubits, better, quantum gates, better interaction between qubits. So there's a huge amount of physics work or kind of physics type work that needs to be done on improving the qubits.
Yeah.
And I think that's where people are focusing a lot of the efforts. But there's more and more, like in computer science or computer engineering, people are thinking about the architecture, the software development kits, and hopefully we can get security also in that, somewhere in those, in that mindset.
Right now, your philosophy is there basically is no security or quantum computers, right?
I think that's not on purpose, but I think that's how people are really focusing on getting them to work, and then not thinking about security, and we're trying to
That don't happen together. Can they be secure later?
Yeah, that's like, so really motivation from our prior work on CPU security, FPGA security is like, if you find a vulnerability in hardware, especially at some point, it's hard to go back and remanufacture everything.
Right.
So if we can convince people to put in or think about security and put in some defenses early on, then it will be already sort of baked in, and then with new generations of quantum computers, they'll hopefully be implemented. So
But with quantum, you're literally looking at re-architecting how the qubits fit together. Like I think you were talking about sort of a square pattern versus
yes,
that increases noise. Help me understand a little bit better.
yeah. So I mean, adding security features doesn't. I don't think it's conflicting with the designs of quantum computers. Uh, a lot of I think the security could be also added at the software layer. So like basically some basic security checks. Before you get a quantum circuit to execute, how is it malicious or is it not? So you could add security at the software layer. You could add maybe some new features at the hardware layer. So, but I think fundamentally, it's not necessarily in conflict that
Okay.
adding more security will make it more, a lot of security could be sort of just monitoring things and let the qubits execute without any extra delay or overhead, but just maybe monitor how they're working. Or were we looking at the quantum computer controller more recently, like do some analysis in the quantum computer controller before you send the control signals to the qubits. So hopefully, hopefully we can find ways of having security features that don't disrupt the qubits, because then people would not add any security features if there's like more power or more area.
Right. So what are you working on now?
So more recently, like I mentioned, so we're really focusing on quantum computer controllers. So a quantum computer controller is effectively an FPGA board, or actually a lot of FPGA boards controlling digital to analog converters and analog to digital converters to send analog pulses to the qubits to actuate them, and then to read out the results. And sort of all the critical data, like what you're executing on the quantum computer, this is processed by the controller.
Right.
So if somebody can attack or extract some information from the controller, they know exactly what you're doing, and they don't even have to bother with like messing with the qubits or the QPU. So our focus on the controller, and I think that's sort of maybe also an easier way to add defenses later.
Right. Do you think it's easier to attack a controller than a qubit?
Probably. I mean, because like for the superconducting qubits, like we look at crosstalk, which is sort of remote, where a user loads a malicious circuit, but like physically opening up a quantum computer, destroys the low temperature, destroys the qubits. But a controller is a classical piece of hardware. So like here at hardwear.io, everybody knows how to hack an FPGA or hack a microcontroller. So attacking a controller, I think it's much easier. I don't think much has been demonstrated, but in principle, it should be easier.
Right. And so one other just final question. If somebody's able to flip the state of a qubit, does that practically speaking allow them to extract any kind of information, or is this more of a denial of service style attacks?
So, right. So theoretically, you cannot clone qubits. So the only way you can sort of extract information from a quantum computer is when you do a measurement. When you execute a quantum circuit and you do a measurement. So if somebody flips a qubit, that will sort of, in the end, might result in the measurement or the final solution being changed. And then so you could be a denial of service where you sort of just mess things up and you get sort of a random output that makes no sense. I think that's what most people have demonstrated so far. Of course, the one ideal goal would be to flip or modify the qubit execution in such a way that you arrive at a solution known to the attacker.
Right.
So then they could sort of control what the victim
Right.
sees.
Right. Well, Jakub, thank you very much.
Thank you for your
Your time. It was a great talk. Everybody loved it.